Hello friends. So today we are going to do few questions that were asked in the 2015. So we have three questions from 2015 mains and we have two questions from 2015 advance. So in totality we have 5 questions. So first one, it was asked in 2015 mains and it states that two coaxial solenoids or different radii carry current I in the same direction. Let F1 be the magnetic force on the inner solenoid due to outer solenoid and F2 be the magnetic force on the outer solenoid due to the inner solenoid, inner one. Then we have to find out the forces F1 and F2, their direction as well as their magnitude. Okay. So these are the two coaxial solenoids. So let's draw an approximate figure for these two solenoid, and we can just represent them with the help of some kind of parallel lines. And suppose this is our inner solenoid and the current will be going from into the one of the wire and coming out from the other wire. Okay, so therefore, and it is all said that the current is flowing in the same direction in both the wires. So we say let this is our into the wire current and correspondingly we have a out of the wire. So this is inner solenoid. Similarly, we can draw our outer solenoid, and the outer solenoid, the direction will be same. So on the top side we are going to have the current which is into the solenoid, and on the other part we are going to have them out of the solenoid. And let us call the inner solenoid as, let's call simpler, P, Q, R and S. So here QR is our inner solenoid and PS is our outer solenoid. So we have QR is inner solenoid and PS is our outer solenoid. And it is said that they are coaxial and current is in same direction. Same current in the same direction. You can see they are coaxial, same current, in same direction, in same direction. And we are given that F1 is a force on the inner to the outer one. Okay, so it means the outer is applying on the inner, that force is given as F1, and F2 is on the outer being applied by the inner. So these are two forces given to us. And so we can say that these are some kind of current elements, and these current elements are parallel with each other. PQ and RS can be taken as current element and they are parallel with each other, current flowing in the same direction, so they are going to attract with each other. And also we know the formula that magnetic field of a solenoid inside magnetic field inside an ideal solenoid is given as B is equal to mu naught N times I, where mu naught is permeability of free space, mu naught is permeability of free space. This small n is number of turns per unit length. Small n is our number of turns per unit length, and I is the current. And for ideal solenoid, we know that the field is confined only in the inside of solenoid, and outside the field is 0. So we know for ideal solenoid, we have that magnetic field is confined inside the solenoid, inside. And second is that outside magnetic field is 0. Outside magnetic field is 0, or we can say magnetic field outside will be equal to 0. And we also know the formula for the force on the solenoid in the magnetic field, that is our D cross, you can say small element dl cross B, and the complete force is the integration of that cross product. So we can write that force on a solenoid in a magnetic field that is given as F will be equal to current integration, we have small element dl and cross the magnetic field, where dl is the small length vector in the direction of the current. Okay. So this dl is small length vector Sometimes this length vector is also called as a current element. Current element in the direction of the current. In the direction of current. So let us discuss force F1 first of all. So you can say force on inner solenoid because of the outer solenoid. Force on inner solenoid, that is our F1, And we just discussed that the solenoid produces a magnetic field which is lying completely inside. It means the magnetic field that is being produced by the outer solenoid will be all associated with the inner solenoid also. Okay. Therefore, we can say that the outer solenoid produces a magnetic field inside itself, which includes the region of inner solenoid. Region of inner solenoid. It means the magnetic field of the outer solenoid will be completely associated with the inner solenoid. Okay. Therefore, we can say that inner solenoid is placed in a uniform magnetic field, that is B. You can say so inner solenoid is placed in a uniform axial magnetic field which is given as B is equal to mu naught n times I, and this is due to the outer solenoid. Due to outer solenoid. So we can use the formula that our F1 will be equal to current is given as I, and we have this dl, and cross we can write here as magnetic field, that is because of the outer solenoid. But the current element dl and the magnetic field outer are both parallel to each other, or we can say both. For example, they are in a z axis. We can take any axis because it is not mentioned here. We can say, but current element dl and magnetic field outer are both parallel. Therefore, we have dl cross B will be equal to 0. So this gives us that force F1 will be equal to 0. Now, second property, or we can say force on the outer solenoid. Force on outer solenoid, that is our F2, and inner solenoid is going to create a magnetic field that will be only inside itself. We can write that inner solenoid creates magnetic field only inside itself. So it means the outer solenoid which lies outside the inner one, the magnetic field because of that is equal to 0. Therefore, the outer, here I have to write it as B outer. Okay, let me correct it. This will be my magnetic field outer is equal to mu naught n times I. So you can see the outer solenoid lies outside the inner one. Therefore, magnetic field due to inner will be equal to 0. So same formula, force F2, current is I, and we have dl cross B inner, and this gives us that our F2 is also equal to 0. So both the forces are equal to 0, F1 as well as F2. So we can say option number D is the correct option. Option D is correct. Now we come to the next question, and it was also asked in the year 2015 mains, and it says that two long current carrying thin wires, both with the current I, are held by insulating threads of length L and are in equilibrium as shown in figure, with threads making an angle theta with the vertical. If the wires have mass lambda per unit length, then the value of I is. So in this case, we have two long current carrying thin wires, and they are held by an insulating thread, and it's in equilibrium. So we have two long wires, and they are held with the help of thread whose length is given as L. So these are two threads, length is given L, and they're making theta with the vertical, and it is said that both these wires are in equilibrium. And we already know that we can just draw an approximate figure for this one part. So this is a fixed point, and this is a thread with a vertical, it's making an angle of theta. So here we are going to have a tension T, and this is our wire. In the downward direction, we are going to have force, you can say weight mg, and this angle will be of theta, and yeah. So let us make, suppose this is the distance r. So we are given that the wires have a mass lambda per unit length, and the length is given as L. So therefore, we can say that these are the two thin wires and both carrying current I. So we can find out the force, magnetic force between the parallel current or the wires which are carrying current. we start from there only. We say the magnetic force between two parallel current carrying wires. Magnetic force between two parallel current carrying wires. And current is given as I. So we can say that the magnetic force per unit length current carrying wires, let me complete this only, current carrying wire per unit length and we can write that our F magnetic due to, and this will be giving us mu naught I square upon 2 pi r. And it is said that the wire is in equilibrium. Okay. So this will be our force, that is Fp, acting on each other. Okay. And we are given as a lambda, that is a mass per unit length. If L is the length, then the mass comes as lambda multiplied by L. Okay. And this L is capital L, not small l. So we can write the equation that equilibrium of each wire So we have total of three forces acting on it. First is our gravitational force. Gravitational force acting in downward direction, and that is our Fg will be equal to lambda multiplied by L and times G. Okay, because it is given as mass per unit length, so this will be lambda L multiplied by G. And then there will be tension in the thread. Which is given as T, and we are going to have our, you can say, magnetic force, that is our let me write it small f. Okay, then I can easily reformulate it. And third is our magnetic repulsion. Which is our capital Fp and will be equal to small fp multiplied by length. So this gives us that our Fp will be equal to, we have mu naught I square 2 pi r multiplied by L. And if we say that the horizontal separation between the two wires is 2x, so if we say that horizontal separation between two wires, let us suppose it is our 2x, so we can write that our x will be equal to L sine of theta and our r which is our 2x, will be equal to 2L sine of theta. Yes, so this has to be up till second wire. Now it says that the forces are in balance, so we can divide the tension force into, so this is our tension T, we have vertical angle theta, so tension T can be divided into two components. Here will be T sine of theta and T cos of theta. In the downward direction we have lambda L G, and towards the right we have our magnetic force, that is our FB. So in equilibrium, for equilibrium we can write that our T cos of theta is equal to lambda Lg, and T sine of theta is equal to our Fp, which is mu naught I upon 2 pi r and multiply by L. So if we divide them, we can write that T sine of theta divided by T cos of theta, this will be giving us a tangent of theta and is equal to mu naught I square, and we have 2 pi r lambda g, and our r is 2L sine theta. So we substitute it, we get our tangent of theta is equal to mu naught I square, we have here 2 pi and this is 2L sine of theta lambda g. Okay. And we can just further solve it, we get mu naught I square, this comes as 4 pi L lambda g sine of theta, and we have to solve it for the current. And yes, so tangent theta, once again we can write sine theta cos theta, then this will be giving us sine square divided by cos, and directly we can write that our current I will be equal to, this comes as 4 pi L lambda g, and we get here sine square theta divided by mu naught cos of theta, and its square root. We can take 4 excuse me please, sine square theta as common, so this gives us 2 sine theta, and we are left with here pi L lambda g and mu naught cos of theta. So this is the value of the current, and the option, the correct one, will be equal to option number A is the correct one. Option A is correct. Now we come to the next question. This question was also asked in the 2015 mains, and it is stating that a rectangular loop of side 10 cm and 5 cm carrying a current I of 12 ampere is placed in a different orientation as shown in the figure below. If there is a uniform magnetic field of 0.3 Tesla in the positive z direction, in which orientation the loop will be in, we would find out the stable equilibrium as well as unstable equilibrium. Okay, and you can say the direction of magnetic field is always fixed, that is toward z, or we can say plus k axis. And the orientation is changing from, first is in zy plane, second one is xy plane, third figure is in xz plane, and the last figure is in yx plane, but the current direction is opposite as compared to figure B. And for equilibrium, we are going to find out the potential energy, and based on the potential energy we can make a conclusion that whether it will be stable equilibrium or it will be unstable equilibrium, depending upon whether the energy is minimum or it is maximum. So we start with the magnetic moment. We say magnetic moment of a current loop, magnetic moment of a current loop, that is given as M, is equal to current, and we have area vector, and where this I is our current, and the area vector, it can be written as A and a n unit vector, and this a n unit vector plays very important part in case of the magnetic moment, because this n unit vector is always perpendicular to the area. Okay. So we say this as a area vector perpendicular to the plane of the loop, to the plane of loop. And in order to find out direction, we can use the right hand rule. Now we mainly require its potential energy. So we can say potential energy of magnetic dipole in a magnetic field. Magnetic field, and that is given as U, and this U is minus M dot B, and we can say that if we have our magnetic moment is parallel to our magnetic field, under this condition energy U is minimum, and this minimum energy gives a stable equilibrium. Stable equilibrium. If we have this M is perpendicular to B, then we have energy equal to 0, and this is called as a neutral equilibrium. Neutral equilibrium. And finally, if we have magnetic field which movement, it is parallel anti-parallel. Now we have anti-parallel to magnetic field. Under this condition, energy U will be maximum, and this gives us unstable equilibrium. Unstable equilibrium. And we are not interested in actually the values. We are only interested in their dot product and the equilibrium type. Okay. So we can just draw a table for that. So we have this as figure number. We can also call it as orientation. And then we have magnetic moment. And dot product. That is our m dot b. And finally is a equilibrium type. So let us start with orientation 1. The magnetic moment is our in plus I direction, and because the magnetic field is always in k direction. Okay. So we can say that the magnetic field is our in k direction always, positive k, and the dot product will be equal to 0. So it means it is a neutral. We have second. Here the magnetic moment is along plus k, and magnetic field is always in plus k. So we get that the dot product will giving us a plus mb. So it means we have this as minimum. And like I said, that u is a minimum, we are going to have stable equilibrium. So we have equilibrium that is stable. Then we have third, and we have minus j. Once again it will be 0, and we are going to have equilibrium which is neutral. And we come to the final, that is our fourth one. We are going to have, and this is our minus k, giving us minus mb, and which will be equal to our plus u max, and it will be unstable. So we are supposed to find out only, you can say, stable equilibrium and unstable equilibrium. So for stable, we have option number 2 is stable, and option number 4 is unstable. So 2 is our stable, so option number B is the correct one. And then we have option number 4 is our unstable. 4 means D is unstable, so this will be stable, and this will be unstable. So we have our option number as one and 3. These are our neutral position. So option number A and 3, A and C are our neutral positions, and we have orientation 2, that is B, is our unstable, and so B is unstable, so this one is correct one. And we have option number 4, that is our D is our unstable. So I mark this. One second. Yeah. So we have this B is stable, so this option is correct, and D is unstable, so this option is correct. Okay. So we can say this won't be here. So option number B is the correct one. Option B is correct. Now we come to the next question, and this was asked in the year 2015 advance, and it states that a conductor shown in the figure carrying a constant current I is kept in xy plane in a uniform magnetic field B. If F is the magnitude of the total magnetic force acting on the conductor, then the correct statement is or are. So basically we have to find out the magnitude of F as well as the direction of your magnetic field from the four options. And we are given this figure. So this figure is basically divided into three parts, so rather we can say four parts. In the first part we have a straight conductor of length L. Then we have a conductor which is at an angle of pi by 6. The length you can see of having radius r, and the next one is also having a radius r but at a different angle of pi by 4. And finally we have a last conductor whose length is given as L, and the direction of the current is same, that is from left to right entire for the entire conductor. So in this case we are given that if L is the length of the conductor, then the force acting on the conductor is our I L cross B. Okay, so we start from there only. So we are given that magnetic force on current carrying conductor, magnetic force on a current carrying conductor placed in a magnetic field, that force is given as F, that is equal to current, and we have this current element L multiplied by the magnetic field, cross product with the magnetic field. So in this, if we see the geometry of the conductor that is given in the figure, we can clearly understand that the wire is shaped as a two-state segment, and the entire thing is aligned on the x-axis, that the direction of current is I, and each is having a length L plus R. Okay, so we can just divide into two parts, entire length. Okay, so this is our first part, length is L plus R, and this is our second part whose length is also our L plus R. And the direction of current is along x-axis, that is I unit vector. So you can see that the wire is shaped with two segments that are aligned along x-axis because of the direction of the current. Okay. And each of length L plus R. It means the total length vector will be equal to, let us call this as L total, and this will be equal to twice L plus R and I unit vector. And let us check one by one the options that are given to us and see whether the force matches with the subsequent option. Okay, so first it states that magnetic field is along Z unit vector, or we can say K unit vector. Okay. So we have option A, and it gives us that our magnetic field is our K unit vector, that is plus Z axis. So we can easily find out our force. So we can say our force will be equal to current I, and we have this L total and cross product with magnetic field. So we substitute the value of L total as well as magnetic field. We get this as 2I L plus R I unit vector, and this is B K unit vector. Okay, and I cross K is our minus of J. So therefore we can write that our F force will be equal to minus 2I B, and this is L plus R and our J unit vector. So of course the force is non-zero. Okay. So from here we can say that force is non-zero and its magnitude will be equal to 2I L plus R, or from here we can say our F is directly proportional to L plus R. So the first option is our correct. You can say option A is correct. Option A is correct. Now we start with option B. Option B gives that our magnetic field is along x-axis, or we can say plus x-axis. Once again, we find out the force is equal to 2I L plus R, and we have this I unit vector cross B I unit vector, and this gives us 0. So it means the force is 0. Force is 0. So option B is also our correct option. Option B is correct. Now we come to the C option. option C, and we have the magnetic field is given as our J vector, that is plus y axis, and we write our force F is equal to 2I L plus R. We have I B cross J, and this gives us 2I B L plus R, and we get this as K unit vector. The force is non-zero, so you can say force is non-zero, and we can say also force is directly proportional to L plus R. So option C is also correct. Now we come to option D, which is along magnetic field along K axis, K unit vector. So we have our option D, which gives us magnetic field is our along K unit vector, and once again we find out our force, and this gives us force is equal to 2I L plus R I unit vector cross B K unit vector, and this gives us minus 2I B L plus R, and we have here J unit vector, or we can just plug this minus with J unit vector. So force is non-zero, is non-zero along negative y axis. So option number D, it says that force should be equal to 0, so this option is incorrect. Option D is incorrect. Now we come to the next question. So this question was asked in the advanced 2015, and the theory or description of this question is quite lengthy, but the solution as compared to the description in the question is quite, you can say, short one, not a big one. So it says that in a thin rectangular metallic strip, a constant current I flows along a positive x direction as shown in the figure. The length, width and thickness of the strip are L, W and D respectively. A uniform magnetic field B is applied on the strip along the positive y direction. Due to this, the charge carrier experiences a net deflection along z direction. This results in accumulation of charge carriers on the surface PQRS and the appearance of equal and opposite charges on the opposite face of PQRS. A potential difference along the z direction is thus developed. Charge accumulation continues until magnetic force is balanced by the electric force. Thus, the current is assumed to be uniformly distributed on the cross section of the strip and carried by the electrons. So this is given as figure, and it says that we have a PQRS, front face as well as back face, and L is the length, and we have given the 2 points K and M, and the first case says that the current is, a magnetic field is applied along the positive y direction. So magnetic field is applied along this direction. So because of this, the charge accumulation takes place on the surface of PQRS. On the front side it will be, and the other side will be our opposite charge carriers. So because of this, there will be a potential difference that will be along z direction. And this charge accumulation continues until the electric force is balanced by the magnetic force. So based on this, we are given, there are two questions based on this description. In the first question, it says that consider two different metallic strips, 1 and 2, of the same material. Their length are same, width are W1 and W2, thickness are D1 and D2 respectively. 2 points K and M are symmetrically located on the opposite face parallel to XY plane, see figure. V1 and V2 are the potential differences between K and M in the strip 1 and strip 2 respectively. Then for the given current I flowing through them in the given magnetic field strength B, the correct option is or are. So in addition, for part A, it has 2 points marked. One is K and another one is M, and they are symmetrical with each other. Okay, and we are given that consisting this as a 2 strips, and the length is same whereas the width is different, and the potential difference between K and M is given as V1 and V2. So based on this, we are going to find out which of the option is the correct one. Okay. And we are given that the current is flowing along x-axis. Current I, it is along x-axis. We have magnetic field that is applied, magnetic field that is our B, and that is along our y-axis. And because of the force, magnetic force, there will be charge accumulation along the z-axis, which leads to potential difference, and this potential difference is also called as a Hall voltage. Okay. And this Hall voltage develops until the magnetic force is balanced by the electric force. So we can say that due to force, charge accumulates along z-axis, along z-axis, leading to potential difference V, potential difference V, and this is also called as a Hall voltage. And across z direction, across z direction. And let us try to understand the physical concept behind this Hall effect or Hall voltage. We can say Hall effect, and that can be easily related with this Hall voltage. Then they are not the same thing, but the effects results in the Hall voltage. And the charges will be our electron. So therefore we can say that the force on a moving charge that is our F will be equal to minus of E, and we have this as Vd, that is a drift velocity multiplied by the magnetic field. Okay. Here this Vd is the drift velocity. Vd is our drift velocity. E is the charge in electron, B is the magnetic field. And it says that electrons drift along x-axis, and it says that electrons drift along x-axis, and we have our magnetic field, that is B, and this is along y-axis. Therefore, our drift velocity cross product B, this will be along z-axis. And it is said that magnetic force will be equal to the electric force, because then only the balance will be maintained. So we have magnetic force is equal to our electric force. So we can write E multiplied by electric field will be equal to E drift velocity multiplied by the magnetic field. So this gives me that the electric field is equal to drift velocity multiplied by the magnetic field. And we only know the relationship between the drift and current. We can say the current I is equal to NE drift velocity multiplied by area. So therefore, we can write from here our drift velocity is equal to current NE multiplied by area, where N is the charge carrier density and A is the cross-sectional area. Here it is a strip, so we can say cross-sectional area of the strip. So we can say N is our charge carrier density, and A in this case will be W multiplied by D. This is cross-sectional area of the strip. Cross-sectional area of strip. And therefore, we can write that our electric field will be equal to I multiplied by B, and this comes as NEW times D. And the potential difference across thickness D is given as V. So we can write that the potential difference, which is our V, will be equal to electric field multiplied by D. And from here we get potential difference V is equal to, we get this as I B, and we have NEW, and this is nothing but our Hall voltage. Now we can just modify this Hall voltage equation according to two strips, strip 1 and strip 2. So we have comparing two strips. We have strip 1, and for strip 1 we can write it as V1, current is same, so I magnetic field is our B1, and here we have N1, E and W. One second. Okay, no problem. I can just readjust it here, and let me solve it first. So we have V1, and we get V2 will be equal to our I times B2, and we have N2 E multiplied by W. So we get that our V2 divided by V1 is equal to B2 upon N2, B1 upon N1, and this gives us B2 N1, and we have this as B1 N2. Okay. So let me fix this one here. One second. Yeah. So this is actually part B, which I messed up once again, like the previous questions which I missed. Let me I think this will be sufficient. Okay, so let us check the options one by one. In option A, we are given that I think yeah, option A, it says that B1 is equal to B2 and N1 is equal to twice N. Then we have to find out what will be the relationship between V2 and V1. So option A, it says that B1 is equal to B2, and it states that N1 is equal to twice N2. So we can write that our V2 by V1, this, let us suppose it is equal to common field B, and we can write this as B divided by B and multiply by twice N2, and here we have already N2. So B and N2 goes away, so this gives us as 2. So therefore we can say that our V2 is equal to twice of V1. So option number A is correct. Option A is correct. And in option B, it says that B1 is equal to B2, N1 is equal to twice of N2, but here it says that V2 is equal to V1. So obviously this option is incorrect. Okay. So you can say option B is incorrect. Option B is incorrect. Now we come to option C. Option C, it states that B1 is equal to twice of B2 and N1 is equal to N2. Let us suppose this is equal to N. So we can write V2 by V1 is equal to B2 times N, and we substitute B1, that is about twice of B2, and times N. Here B2 and B2N cancels out, and this gives us 1 by 2, which tells that our V2 is equal to 0.5 times V1. So our option C is our correct. And in option D, obviously for the same data, it says that V2 is equal to V1, so option D is incorrect. You can say option C is correct. C is correct, and option D is incorrect. So this was our part B. Okay, so this was our part B. Now I'm going to solve part A. Okay, and for part A, we have to once again try to understand here. Rest of the things is same. Only thing is that current is in I direction, that is x-axis. Magnetic field is in B, that is our y-axis. Okay, and under equilibrium, so we can say once again, because of the electron, they will be moving towards negative z-axis, and this will be creating a Hall voltage, that is VH. Okay. So you can say that magnetic field is along plus y-axis, therefore electrons experience force deflecting them along minus z direction, and this process is going to continue, and that will be result in developing of the Hall voltage, which is also denoted as V of H. And at equilibrium, the force due to magnetic field will be equal to force due to electric field. So therefore we can write the electric field force is equal to E drift velocity multiplied by the magnetic field. And here this Vd is our drift velocity. So E and E cancels out, and we can say that the Hall voltage that is above VH will be equal to electric field multiplied by distance d, and this gives us a Vd B multiplied by d. And we already know the relationship between the current and drift velocity. we can say current I is equal to NE VD, and we have area will be equal to our W multiplied by D, and this gives us that our drift velocity VD is equal to current divided by NE W times D, and we substitute it in the hall voltage. One second, this is our drift velocity, so let me change the notation VD, and here also, and here also. So this is our VD and this is our VD. So therefore we get the hall voltage which is our VH. We can write this as INEWD and multiply by magnetic field and D. Here D and D goes away, and we can write here that our hall voltage is proportional to magnetic field and N. Now we are going to compare the two strips. Okay, here N is carrier charge density. N is our carrier charge density. So comparing two strips, and in this question the hall voltage is just represented as V, so we can just call it as a sake of convenience as V. And for two strips we have strip 1 and then we have a strip 2. Strip 1 we can write our V1, that will be directly proportional to B1 upon N1. Then we have V2 proportional to B2 upon N2, because in this question it is given that we have different thickness and different width, okay, and you can say V1 and V2 are the potential differences. So here let me check, the widths are also different. Okay, so we have to modify this. So you can say it is proportional to, we have our B and there is no D, so D doesn't matter, and we have different width, that is our W1 and W2. So we have our B and we have our N and we have our W. So this we can write here W1 and here we can write a W2. Therefore we can say that width doesn't matter. Let me check. VH is equal to D yes, correct. So let me take the ratio and we can write that V1 upon V2, this will be giving us V1 upon W1 N1, and we have this as V2 upon W2 N2, this giving us B1 upon B2 multiply by W1 N1, and here we have it as magnetic field is same in this case. Yeah, same magnetic field. This is not required. So we can write this will be equal to our 1 upon W1 N1, and we get 1 upon W2 N2. So this will be equal to W2 N2 and W1 N1. Okay. And we can check the options that are given to us. So let us start with option A, and in option A it is mentioned that W1 and W2 are equal, and D1 D2 doesn't matter because there is no D here present. So it states that W1 is equal to W2. So we have W1 is equal to W2. Let us suppose that is equal to W. So we can write that our V1 to V2 will be equal to W into N2, W into N1, and W cancels out. So this gives us N2 upon N1. So in this part there is, you can say, 1 second. Yeah, so here this electric field, it has to be W, not a D. Okay, because the cross section that which we are going to take, which is being multiplied by electric field, it's always taken normal to the direction of flow of current. That was mistake. So this comes as W, not B, and here also it has to be W. This will go D, and this W cancel with W. Okay. So now we can just write this entire thing again. Okay, let me first complete it. So here we get that our hall voltage, that is VH, will be equal to I multiplied by magnetic field, and this is our NE multiplied by D. Now we have two strips. So we have here two strips, and therefore we can write this is equal to our V. Therefore for strip 1 we can write that our V1 will be equal to I B N E, and we have 1 upon D1, and we have strip 2. So this gives us V2 is equal to I B N E, and this comes as 1 upon D2. Okay. So in option A, we can divide these two terms. We get V1 upon V2 will be equal to D2 upon D1. Okay. And in option A, it gives us that W1 is equal to W2 and D1 is equal to D2. So for we have so we have our option A. Option A is our W1 is equal to W2, and we have our D1 is equal to twice of D2. The equation doesn't contain any W, so we can say straightforward that V1 upon V2 and D1 is our twice of D2. So if we substitute it, we get this as D1, this is our D2, and we have this as twice of D2. D2 and D2 goes away. So this gives us that our V1 is equal to 1 by 2 times V2. And option A, it says that V2 is equal to twice of V1. V2, yeah. So we can say from here V2 is equal to twice of V1. So option A is correct one. Option A is correct. Now we have our option B. Obviously option B will be incorrect because that says V2 is equal to V1. Okay, so from here we can directly say that option B is incorrect. Now we come to the option C. And option C gives us that W1 is equal to twice of W2, and we have D1 is equal to D2. But W1 and W2 are nowhere in the picture. Therefore, we can write that V1 upon V2 is equal to D2 upon D1. So they are same, so we can say D2 upon D2. These two cancels out, so this gives us that our V1 is equal to V2. So option C is incorrect. Option C is incorrect. But under the same condition, we have the answer in option D. So we can say option D is correct. So here option A and D are correct. Option A and D are correct. Option B and C are incorrect. So here only one thing we have to remember, that we have to take the electric field should be multiplied by the W, not by D. Okay, so reason is simple. Let me write it here, that area of cross section is always taken normal to the direction of current flow. Normal to the direction of current flow. Okay, this was slight problem. So this completes all the questions that was asked in the year 2015. So there were 3 mains questions and 2 were of the advance. So this completes all the 5 questions. Thank you.